For the Pythagorean theorem, we were looking at one of the classic results of geometry as a whole, not just for triangles, where if we have a right triangle like so, with side lengths A, B, and C, where we call the long side there C the hypotenuse and the shorter sides the legs, we have that the relationship between the side lengths is going to follow the formula a squared plus b squared equals c squared. And despite what many people, such as Shaquille O'Neal, may say, and what many of you may also, for that matter, feel, well, the Pythagorean theorem isn't quite as complicated or as bad as you might think, despite the fact that we've got 3 letters in there and 3 exponents in there. By the way, there's actually a very special thing that this does not happen very often. It took quite a lot of work to prove that, but that's a discussion for a very different class. Anyway, with the Pythagorean theorem, this can actually be pretty intuitively shown in terms of the fundamental relationships that I mentioned earlier about what goes on with triangles, and in particular right triangles, and the areas of rectangles. But talking about areas is getting a tiny bit ahead of myself. It's a tiny bit ahead of where we are right now. Just know that this has some fundamentally approachable logic underneath it, as long as you think of these things in terms of the shapes you might get if you shoved 2 right triangles next to each other in the right way. You get a diamond otherwise, and that's not very helpful. But anyway, hopefully you're getting some of an idea of how this works. For a bit of history, we credit the Pythagorean theorem to Pythagoras, as the name would hopefully imply, the Greek mathematician of the 6th century BCE. But despite the fact that we use a lot of the notation that he helped codify,
I wish I was high on pot news.
There's actually quite a bit of historical evidence that the idea of the Pythagorean theorem is even older than that. It is properly ancient, with some texts showing ideas of the Pythagorean theorem being dated back to the 2nd millennium BCE, that is, the year 1500 to 2000 BCE, 1,000 years earlier, in ancient Egypt and Babylon. So this is a thing that people have had an understanding of for quite a long time, and I guess from some of your perspectives has been confusing people for quite a long time. Where another quick bit of history for this, I know the word hypotenuse sounds silly.
That was my joke. I know, man, that was hilarious.
But it actually does come from a bit of a etymologically sensible place, where the word comes from Greek meaning stretching line. That is, it's the line that stretches under, and that makes sense if we look at this diagram there, but spun around a little bit. So you have the right angle on top with the legs adjacent and opposite to your other angles there, thinking in terms of some trigonometric language that is hopefully scattered in the cobwebs at the back of your mind. And then that means that the hypotenuse, the third, not leg there, side length, is stretching both underneath the right angle and underneath the other angles as well. But we can go back to the standard arrangement there that you're probably more used to it in that upright position, and then look at an example here for why we might care about the Pythagorean theorem. A little bit of a applied context for what we have here to go with the history. Generally speaking, the size of a screen is given in terms of diagonal length, which can be seen as the hypotenuse of a right triangle formed by the sides and a line segment from the opposing corners. Use this to find the size of a screen with side length 18 and 24 inches. So what we can do here, what we can use the Pythagorean theorem for, is to get an understanding of, well, how a TV might fit a space that we have. So let's say that we have something like that, where, yeah, I can't draw to scale. Congratulations, we're going to learn that lesson pretty well by the end of this unit in particular, if you somehow haven't already. But let's say we've got a screen like that, and let's pretend I drew it to scale, and let's even make things more interesting by pretending there might be something cool going on that screen. So we have our lengths here 18. Actually, this one's longer, so I'll say this one's supposed to be the 24 inches, and that one's supposed to be the 18 inches. And if we want to get the diagonal across that there, we can dot that in, get something a bit like so, where we can think of this in terms of that right triangle with this as our value c. That's our hypotenuse. So, by construction, we have that c squared is going to be equal to a squared plus b squared. And it doesn't really matter which one we call a and which one we call b, as long as we know those are our side lengths. 18 squared and 24 squared, where thankfully I have those written down here for me so I don't have to remember it. That 18 squared is 324. Well, I could do it in my head, but that would be slow and not very fun to watch. And meanwhile, 24 squared is 576. So we add these up. We get a value of 900, which means that C, the size of the TV as it were, is 30 inches. It's not a very big screen by today's standards. Maybe it's something you'd want for a small computer monitor if we're being honest with ourselves. But hey, that's what we've got for this example here. And in particular, this is a case using similar triangles of a very special kind of right triangle, because if we multiplied 6 by 3, we get 18. If we multiply 6 by 4, we get 24. If we multiply 6 by 5, you get 30. So this is a thing called a 3, 4, 5 right triangle, which again is hopefully reminding you of some very special and important things that we're not going to see until nearer to the end of the chapter. But for now, we're going to move on to our third section, our last one for this week. We're going to talk about some more general geometric ideas, some more general geometric shapes, getting a sense of our polygons and the things we can do with them, the things we can identify from them, and all of the other flavors of shape with angles and sides more than 3. That's what we got next.